mailing list, or also the link will also be provided in the chat box. Now it's my pleasure to introduce Dr. André Artelt, who is our speaker. Dr. Artelt is a postdoctoral researcher at the Machine Learning Lab in Bielefeld University. His research focuses on trustworthy AI in critical infrastructures, making his insights extremely valuable for water engineering domain. You can connect with him on LinkedIn and also follow his work on GitHub. Also, by the end of the talk, we'll have some time for questions and answers, so feel free to drop the questions at the chat box. And with this, I would like to hand the floor over to Dr. André. Now, the floor is yours. Thank you.
Yeah, thanks a lot for the nice introduction, and also a warm welcome from my side. So I will just set up the presentation on my side. Give me just a second. So you should be able to see my my presentation, right?
Yes, we can.
All right, so then let's start. So as already announced, today's webinar will be about explainable AI for event diagnosis. And obviously, we are focusing on water systems here. Now, to be a bit more specific, the plan is as follows. So first of all, I will start with a very brief introduction to explainable AI, in particular on something called counterfactual explanations. And then I will move on to apply those introduced techniques to interpretable event diagnosis in those water systems. And then finally, I will conclude today's webinar with a hands-on session in Python, where I will basically show you how to implement the things for the event diagnosis in Python. In particular, I will show you some basic implementations of counterfactual methods for event diagnosis. And also, I will make those slides that I'm going to show you, I will make them available. So in the very end of my presentation, there will be a QR code, and I will also put a link in the chat box of the Zoom meeting where you can download the slides, so you can later on take your time and revisit some concepts, or maybe also click on some links that I have in my presentation. Okay, so with that having said, let's move into explainable AI. And here I really want to emphasize that this is a very brief introduction, so we don't have time to talk several hours about that. But I will also link you to some resources where you can learn more about explainable AI if you're interested, or if you want to explore some of the concepts that I'm going to present in more depth. Now, let's start with a brief motivation. So I think nowadays we are all aware of AI-based systems, and probably many of us have contact with such systems on a daily basis. So I guess ChatGPT is something everybody has heard about so far. And there are also other AI-based systems, like, for instance, camera tracking systems, where like the camera is supposed to focus on an object of interest, like here depicted on the right-hand side, where the camera has to focus on a soccer ball. Those tasks are also increasingly automated by AI systems. Now, AI in general shows an impressive performance, and it seems to get better every single day. However, it is still far from being perfect, and it still makes a lot of mistakes. Like in this case here on the right-hand side, where the camera suddenly starts to focus on the referee instead of the soccer ball, which of course is a bit annoying. And whenever those things happen, of course, people ask why. People want to understand the reasoning of the AI system. And this is where explainable AI comes into play. Now, explainable AI is a human-centered domain, so to say. And this is why it is really important to think very carefully about what we want to explain, and in particular to whom we want to explain something. So in the XI community, we often refer to like a table like this one, where we have different people or different audiences, and also highlighting the different goals, what they have in mind. So for instance, you might be able to imagine that like engineers might have very different goals from, let's say, regulation authorities. So the engineers might be mainly interested in understanding in order to improve the given system, whereas the regulation authorities might be more interested in justifying something and in also understanding the legal implications of something. And this is why it's really important to pick the right tool in the right situation. And there really doesn't exist a single technique that is able to always work, or that is always the best choice. You always have to very carefully think about the use case you're dealing with. Now, what tools do exist? There exist a lot of possible XAI methods and tools. And here I have a slide trying to introduce kind of a taxonomy of existing XAI methods. And you can see, like, we have untalk methods, which are basically methods that claim to be inherently explainable. So the system by design is already interpretable or understandable in some way. On the other hand, we have some things like post-hoc explanations, and those are methods that explain the output of a system after we observe the output. So we kind of want to justify the output of the AI system. And this is actually a very popular branch of XAI, and there's a lot of research going on, and there already exist many methods there that are ready to use for, in some sense. And one popular sub-branch of those post-hoc methods are feature importance methods, and there the idea is basically to quantify the importance or the influence of specific input features. So you might have heard about methods like LIME, where, for instance, the idea is to approximate a highly complicated model by a simpler model that is easier to understand, like a linear model or also like decision trees. There also exist Shapley values, which are probably one of the most popular XAI methods nowadays. And there you basically want to estimate the influence of a particular feature on the output of the AI system. So some features might have a positive impact on the outcome, whereas some other features might have a negative impact on the outcome. And then another method are the so-called counterfactual explanations. And those are the explanations that we are looking at in this talk. Now, counterfactual explanations are in some sense contrastive explanations because they tell us how we can change the outcome of the system. And this is a very natural way of explanations to us humans because it basically mimics the way how humans explain things. And to make things a bit more clear, we can come back to this example where the camera is supposed to track the soccer ball. But at some point, the algorithm, so the AI system deployed here, starts focusing on the referee. And this, of course, is annoying because obviously in a soccer match, the interesting part is wherever the soccer ball is. This is where the action happens, and not the referee standing on the line. And how could an explanation look like in this case? So a counterfactual in this case could be something like that. It could say if the referee had hairs on his head, then the AI would have not mistaken the referee's head for the ball. And you can already see, like, this is very similar to how we humans would explain things. And this is also where the popularity from counterfactuals comes from, basically, because it's easy and intuitive to us humans. You don't have to study math or computer science in order to understand a counterfactual explanation. Now, counterfactual explanations must be then obviously formalized if you want to use them in practice. And there are two basic properties that must always be satisfied. The first one is the so-called contrasting property. And this property basically states that the outcome of the system must change. And the second one is then often referred to as the cost or complexity of the explanation, which basically says that we want to have an easy and simple explanation. And here on the right-hand side, I have a toy example, which you will see a couple of times from now on, where I have a simple classification task. So I have a red area and a blue area, meaning that every point within this red area is classified as red. So in this case, it's class 0. And every point within this blue area is classified as class 1. And now we have a point in the red class. So this X original is classified as red. And we want to understand how we can turn the classification into blue. So we want to move this point in red to a point in blue. And this was first formalized as an optimization problem by Wachter et al. In 2017, kind of starting the field of counterfactuals in explainable AI. And in my presentation, whenever you see such a blue reference here, it's clickable. So you can click on this reference and then you can read the original paper in case you want to learn more. And now what Wacht et al. Did is they formalized it as a simple optimization problem. And in this optimization problem, again, it's an illustrative example. We keep things simple and just assume we are working in the real-valued vector space. So of course, in some application domains, those might be not real numbers, but I don't know, natural numbers or whatsoever. But they use the real numbers. So, and this optimization problem, it consists of two terms. The first term is the contrastive property. So all this term basically says is that the counterfactual explanation, so after moving the red point around, must have the desired classification. So in this case, it says, okay, it must become a blue data point after moving it around. Now, the second term in this objective is then referring to the cost and the complexity of the explanation. So it basically tells us that out of the many existing explanations, we prefer the most simplest one. And as you can already see on the right-hand side, there exist multiple ways how we could move this red data point into the blue area. So in this case, I just depicted 3 of them. There might be even more. There might be infinitely many, depending on how we formalize the data domain and the classifier. And in this particular example, we might say, okay, we just use the Euclidean length as a measure of cost or complexity. And then this one might be the optimal counterfactual explanation in this particular setting. Now, an alternative to this formalization would be to formalize this optimization problem as a constraint optimization problem. So it's basically equivalent, but it's just written a bit differently. So here we have now the objective is to minimize the cost or complexity of the counterfactual, so of this XCF, such that the counterfactual indeed changes the outcome of the system. Yeah, and in some applications, this optimization problem is easier to solve. In some other, it's more beneficial to solve this one. It really depends on the case you're dealing with. Now, those two aspects are the basics, but they are not the only aspects that are important when it comes to counterfactuals. A really important aspect of counterfactuals is that they are not unique. So there might exist more than one possible explanation to explain a certain outcome, as depicted here on this cartoon, where we observe a broken bottle, and there are 3 individuals, so in this case 2 humans and 1 dog, and they all have different opinion of what might have happened, such that we now observe this broken bottle. And all explanations might be plausible, so they all explain equally well what happened. And if this is the case, then of course it raises a question, which of those explanations should we select? Which of those explanations should we present to the user? So sometimes this missing uniqueness, which is also called Rashomon effect, can be a challenge, because if you have infinitely many explanations, you have to introduce some additional constraints. Otherwise, it's just infeasible working with them, because nobody wants to look at 1,000 explanations. On the other hand, sometimes it can be also a blessing, so to say, because it gives us some flexibility in how we implement the change. So you can imagine in the context of loan application, if your loan application got rejected, it might be nice to have actually different explanations on how you could turn your rejected loan application into an accepted one. So there it might be actually beneficial to have like a variety of possibilities to choose from. Now, another crucial aspect is that counterfactuals, because they are often executed or to be executed in the real world, they must be plausible and realistic. And in this case, it can be problematic if this is not guaranteed. For instance, here I have an example of a 9. So this is a digit which is supposed to show a 9. It's a bit blurry, but I guess we all can agree that this looks like a 9. And now if I ask the system what I have to change in order to make it a 0, if the system then comes up with something like that, this is not really plausible. So this does not look like a realistic 0. It still looks like a 9 with a weird dot over here. So this is an example where the counterfactual is not meaningful at all. And another issue, or a potential issue, is causality. Because the world around us is it's a causal world in some sense, because there are dependencies everywhere. So you often have that, like, some variables depend on some other variables, and some values imply some other values. And of course, if we are talking about counterfactuals that are to be executed in the real world, then they should be causal, because otherwise they are just infeasible to execute. And those points actually must be considered when computing counterfactuals in practice, and also a few more, but those are the most important ones. Another thing I will only slightly touch upon in this talk is the issue of robustness. This one can also be important, particularly when handling uncertainties. And I think uncertainties is something that we observe in practice when dealing with real systems quite often, because often when we take measurements in the real world, there's always like some kind of noise or uncertainty involved. And not only the models, so let's say the AI systems, have to deal with it, but it might also be necessary that the explanation method, so in this case, the counterfactuals, have to deal with this. But I will not go too much into detail of those, just a little bit. Now, plausibility and actionability, as already said, those can be an issue, because a missing plausibility significantly hinders their usability in practice. And again, like I have here this example of an adversarial attack, which turns a 9 into a 0, but it's not meaningful at all to us humans. So what can we do about this? And I want to present two methods for that. But first of all, we have to think a bit more carefully about where this problem comes from. And the main source for those problems of missing plausibility, but also missing causality, is that many counterfactual methods actually assume feature independence. And this means that the method assumes that all the features can be changed simultaneously and independently of each other. And this, of course, is a very strong assumption, which often does not hold. I mean, in our case, we are here talking about water systems. We all know about the relationship between pressure and flow, so we cannot change things independently there, for instance. And also in many other real-world settings, we do have like kind of things like a causal graph, where basically variables have dependencies, and we cannot change everything independently. And this is actually a main issue that many methods overlook. However, a few actually try to go into this direction, do something about it. And two methods that I want to talk about very briefly about are phase and their density constraints-based method, which I developed many, many years ago. Now, the density constraint methods, basically, it's a very simple idea, but it turns out to be very powerful and very beneficial in practice, because there we add an additional constraint to the optimization problem. So here you can see we have our objective that we want to minimize the cost or the complexity of the explanation, such that the outcome of the system changes in some desired way. And now I add an additional constraint to it, namely a constraint on the density of my final data point. So I require that my final sample, after applying the modification, lies in a region of high density. And this was shown to not only result in plausible counterfactuals, but also was shown to improve the robustness. So everything becomes more stable with respect to uncertainties. It does a good job when it comes to those plausibility and realistic or realism constraints. It still has some drawbacks when it comes to causality, because there is no real causal model implemented here. You can define this density function in such a way that some constraints can be satisfied, so like some dependency constraints, but it cannot satisfy arbitrary constraints. So this is a drawback of this method. Nevertheless, it's a very simple and beautiful approach, and it gained some popularities over the years. So people are still working in this area of using density constraints to ensure plausibility and actionability. Another popular method is a method called phase, which stands for feasible, actionable, counterfactual explanations. And this is also a very interesting method, because it's very different from the existing ones. So here the idea is, instead of moving from the red area to the blue area in one step, it goes stepwise. So it first goes to a nearby point, it jumps to the next nearby point, and so on until it crosses the decision boundary. And this method assumes actually that we have a data set given. So we need such a kind of a database of cases, so to say. And then, of course, it needs some definition or some notion of what is a feasible jump. So is it feasible to go from here to there, but not from here to there? Maybe this is too long, but this needs to be formalized in some way. But if it can be done, then this is a really interesting method, because it goes away from like changing everything in one step, and it can incorporate those dependency constraints much better than it can be done by the density constraints. So this is also an interesting method. And again, like, you can click on those links and then you can read more about those methods linked there. Now, another issue, as I already mentioned, is robustness. And robustness is something that can go wrong on several levels. So for instance, we might have changes in the input space, so like input perturbations. And this, of course, could become a problem, because if we have a data point here, and let's say the optimal counterfactual would be here, if we again assume Euclidean space. Now, if I move my data point a little bit to the right-hand side, the optimal counterfactual suddenly is here. So there's a huge difference between those two samples, although the original samples were quite similar to each other. And this, of course, is a problem, because it's very sensitive to the input, which in case of uncertain inputs might become a problem. And other things are also a model change. So for instance, if our models, our AI system is changing over time, then those counterfactual explanations might become invalid over time. So if, for instance, we had this dotted line as a classifier, our counterfactual just moves this point over the decision boundary. But if now our decision boundary changes a little bit, the counterfactual is no longer valid. And this, of course, is also unfortunate, because usually those AI systems do change over time. They are retrained, they are further improved. But on the other hand, the user, they need time to execute those counterfactuals in the real world. So they cannot instantaneously make all those changes that are recommended to them. And then lastly, there's also a problem with respect to integrity of the data set. So it was shown, and this is what I did last year, that we can manipulate the training data set that is used for training the AI system, such that we can manipulate the counterfactuals that are built on top of that. And this, of course, is really bad, because in scenarios where we cannot guarantee the integrity of the training data set, we might not be able to trust the counterfactuals. The counterfactuals might be correct, but they might be no longer optimal. And this is also a challenge that came up recently. Now, what can we do about it? We can do a lot about those methods, but I don't have time to discuss all those things in detail. So this is why, again, I put some references here for you to read about. As already mentioned, one popular approach for increasing robustness is by using those density constraints. They indeed show an improvement in robustness if used correctly. Another approach is something to aim for min-max objectives. So here we have a data point X, and instead of just computing counterfactual that is valid for this data point, we are computing counterfactuals that are valid for all the samples within this neighborhood of this data point, which means that this one is not valid, because those points in the white area here, they are still not in the gray area. So those are still misclassified in some sense. Instead, we have to move further to something like that, where all the points in the neighborhood are also classified correctly. And there exist many other methods what can be done, but as I said, in the interest of time, we don't have time to discuss those in further detail. Now, to sum up, Explainable AI is about understanding the reasoning of AI methods. And maybe it's also the right point to mention that although those tools are developed for AI systems, they can be usually applied to many other systems as well. Because nowadays it's sometimes a bit philosophical whether a given system is really an AI system or not. And this definition of AI is also changing over time. But those tools, they can be really applied to other black box systems that we want to understand. And in the very beginning, I really highlighted or emphasized the thing that there doesn't exist a single XAI technique that is doing the job in all situations. So it really comes down to picking the right method in the right situation. And then we talked about counterfactual explanations, which are my favorite type of explanation and also a very popular one. And those counterfactuals basically they tell us how to change the outcome of a system. And they're very intuitive to us humans, as I tried to demonstrate with this example of the camera focusing on a soccer ball, but then it was mistaken the referee's head for the soccer ball. And those counterfactuals, it's a research topic on its own. So I briefly touched upon aspects like plausibility, actionability. Very briefly, I mentioned robustness and the link to uncertainties. And there's much more to be discussed there. But yeah, this is not a talk about counterfactuals, but more like counterfactuals applied to something. And this is why I put here some links to two tutorials, which I gave with my colleagues last year and in the beginning of this year on counterfactuals at major AI conferences. And if you want to learn more about counterfactuals, I would suggest you click on those links and you check out the material there and start reading. There's still, yeah, many more aspects where you can learn more about if you want to use counterfactuals in practice. Now, this concludes the first part of counterfactuals. And now we are moving into event diagnosis in water systems. So in a water system, and I think most of the people in the audience know much more about water systems than I do, we actually have a very complex and complicated system to operate. And the complexity basically does not only come from the size of the system. So here I have a picture of L-Town, which most of you might know is a popular benchmark nowadays in the community. And but the complexity also comes from the huge amount of uncertainty that we are facing. And one source of uncertainty is, for instance, sparse sensor placement. So we usually only have very few sensors in such large networks, leaving most of the parts of the networks, yeah, basically unmonitored. So we don't really know that much about it. But if you want to operate the network, we have to estimate whatever's going on there. Then, of course, the sensors might be also noisy and also some other important characteristics of the network, such as the water consumption behavior, might be also subject to uncertainties. And this is what makes operating such a network really challenging. And when it comes to event diagnosis, usually event diagnosis means that we want to be able to detect events. So we want to detect anomalous behavior in the network. And then we, of course, also want to analyze those events. So this could, for instance, mean that we want to be able to detect and localize leakages. Obviously, we have to identify faulty sensors because those sensors are basically our senses. This is how we perceive the network. But also other things like, for instance, contamination events or cyber physical attacks are things that we want to detect such that we can react to those. And how this is usually done is it's done by human judgment and experience. So often there are people in a control room sitting in front of monitors, and they're looking at the sensor readings, and then based on their experience and based on their knowledge, they make decisions and they try to understand what's going on. And what people are doing, and this is also in line with what we are doing right now, we want to develop tools that support those humans. And I really want to emphasize here that we want to support the humans. We don't want to replace them. I think replacing them would be insane, in particular in those critical domains such as water systems, but also in power grids. There are already like subtasks that are automated, but I think aiming for complete automation, it's just crazy. I think we should not do this, definitely not. Now, when it comes to event diagnosis methods, one might be tempted to say that AI is now a new tool that allows us to do things that we were not able to do before. And to some extent that might be right, but it's also important to acknowledge that event diagnosis is not a new field. I mean, event diagnosis has been around for several decades already, and many methods already exist that try to detect anomalous behavior. And when it comes to AI-based methods, I often like to think about them as data-driven methods, because then it becomes a bit more related to what already exists. Because data-driven methods themselves, they are not really new, but they are experiencing a huge boost because more and more data is available nowadays, and also compute power is now much more available than it was like a couple of years ago. And one very popular method for doing those event detection or then also event diagnosis systems is are residual-based methods. And those residual-based methods, they are also very intuitive to humans. Because the way how they work is basically we have an expectation or a prediction of like how the system should evolve or how things should look right now. And then we have the observations on the other hand, and we can compare those two worlds. And whenever like our expectations and what we observe deviate too much from each other, then we might suspect that something is wrong or something unusual is going on in the networks that we just missed. And then this is when you would raise an alarm. And just to make things a little bit more formal, we can think about this, that we have a function f, which takes some inputs, could be previous sensor readings, could be something else. And this function then makes a prediction of how the system state should look right now. And then we compare it to how the system looks actually right now, so with our sensor readings. And then we compare those things like we do here on the right-hand side. And whenever the difference is small, everything is fine. But when it is larger than some threshold, like after this red dotted line, then we raise an alarm, because then our prediction and our observation, they deviate too much. And then we might have to dig into the reasons for this. And this function f, it could be really anything. So it could be like a simulator, it could be surrogate models, it could be like some forecasting method using fancy AI methods whatsoever. It doesn't matter at this point. It's really the core idea that like we observe something, we predict something, and we compare it, and whenever those two deviate too much, then something unusual is going on. Now, having such a method, of course, is great because then we can perform event detection. So we can flag anomalous behaviors. However, depending on how this function f looks like, it might not be clear how it works. So it could be, for instance, a complicated neural network or some other complex method that is difficult to understand. And then, of course, if we cannot understand how this function works, there might be trust issues. So humans, let's say the human operators, for instance, in the control room, they might not trust the output of the system. So the system might say, okay, I believe something unusual is going on. Please do this and that. But because in critical infrastructure, I mean, as the name suggests, it's like a critical domain. Those things have severe consequences or potentially severe consequences in the real world. So people might be hesitated to execute actions that they do not understand. So an obvious goal is then to make those event detection systems more transparent, such that humans can inspect their internal reasoning and can better understand of how they came up with their decision. And now we are coming closer to the main topic of this talk. We want to use explainable AI, or we want to use techniques from explainable AI to make those event detection systems more transparent. And now again, remember what I said in the beginning. Before applying some XAI technique in this context, we first have to think what we want to explain and also how we want to explain things. Now, obviously, what we want to explain should be pretty obvious, because we want to explain the deviations. So we want to explain why there's a large deviation between the observed value, so this blue line, versus the predicted line. What is causing these deviations? this is what we want to understand. And this is already kind of a contrasting question, because we're basically asking, okay, why is the orange line here but not there? Or the other way around, if you wish. And when it comes to contrasting explanations, the first thing that one could do is one could study the feature importances and in particular their contributions to the outcome. So we could, for instance, use a tool like Shapley values and perform kind of a sensitivity analysis in the sense that we could investigate the influence of, let's say, past pressure readings on the observed outcome. And this could be already on its own valuable insight. However, it does not really explain what's going on in the system. It would be more like a technical analysis of some properties of the system, but it does not perform any reasoning on a higher level. And for this, we could use counterfactual explanations, because we really want to understand what was the reason behind this, and not understanding some sensitivities of the event detection system. And for counterfactuals, for instance, we might then generate explanations like that, okay, a sensor fault is responsible for this deviation. Or maybe there's a leakage at some node in the network, which in this case, results in the drop of pressure. Maybe there's also a change in the water consumption behavior, or maybe something completely different. And here again, you can already see that there might exist multiple explanations of what is going on. And, like just from looking at this plot, it's really difficult to tell which of them might be the correct one. I mean, they might be all equally correct. It's hard to tell. And what then in practice, what one could do is one could generate like a set of those different explanations and give them to the user and tell them, okay, I have a few hypotheses, what's going on in the system. Now, please take this knowledge and do some further investigations. Or in addition, what could also be done is we could also compute kind of a likelihood for each of those things. So how likely is it that we have a sensor fault versus how likely is it that we have a leakage, for instance. But it's really important to keep in mind at this point that when we go for counterfactual reasoning, we have to keep in mind that there might exist multiple possible explanations, and we might not be able to select the true one, because we just don't have all information available that we would need in order to do so. Now, what does it mean to reason over alternative worlds or alternative scenarios in this context? Well, because this event detection function, this function f, it relies on some inputs and assumptions in order to compute the prediction. And as I already mentioned before, those things could be, for instance, past sensor readings or other sensor readings. It could be some estimates, for instance, demand estimates, but also parameters of hydraulic laws or some assumptions about the topology of the network or whatsoever. So all those things goes an input into this function when it predicts the system state somewhere. And now when we want to compute a counterfactual, when we want to do this reasoning, then this basically means we have to change the input. So we have to change those things in order to change the outcome. And then doing this counterfactual reasoning basically means we have to identify the most plausible changes in those parameters, in those inputs to our event detection system, such that the difference basically disappears. So such that those two lines align again. And this is then the challenge that we have to tackle on an algorithmic level. Now, more formally, this means, again, we have our function. We have maybe some things we take as an input from sensors. And we have other assumptions, as I just said. And then this becomes an optimization problem that we want to solve. So we want to find new inputs, so new other or past sensor readings, and also maybe some changes to our assumption, such that the difference now is below the threshold. So it's in an acceptable range where we would not suspect any anomalous behavior going on. This is the optimization problem we would have to solve if we want to compute a counterfactual explanation in those scenarios. Now, in our paper, and I put here a link to to a preprint for you, so you can already read a little bit about this. What we did is we implemented this event detection method as a set of virtual sensors. So basically, we have one sensor that tries to predict all the other sensors, and then we get a system where, like, for each sensor, we have a prediction and obviously observation, and then we can do our residual-based event detection. And in our case study, we also focus on only two types of events, namely leakages and sensor faults. And we want to distinguish between those two types of events. So we would not only be able to say, like, okay, there is something, but we also want to say, okay, this is a leakage or this is a sensor fault. This is also something that we want to do. And then we did some experiments on simulated data. And in this case, we considered L-Town and Hanoi. And on the next few slides, I will go a little bit more into detail into this case study of, like, how we can implement this optimization problem and also how we can solve it, and then how the results look like. Now, before talking about the results, we have to talk about how to implement this event detection method. So just as a quick reminder, we have now a set of virtual sensors. So for each sensor, we have a virtual one. This F is our virtual sensor. So it tries to predict how the sensor value should be. And then we have the actual sensor values. We compare them, and whenever the difference is too large, we raise an alarm. Now, because we have now a set of virtual sensors, we have a set of models, we need a concept that basically carries counterfactuals over to multiple models. And for this, we can use something called ensemble consistent explanations. And this is something that I developed already a couple of years ago. So this was done in 2022. And here, basically, the idea is that we compute a single explanation that is valid for all models. And then in the context of this event detection system, we use this explanation as kind of a fingerprint of the observed event. And then we can do reasoning over those fingerprints. So we can say, okay, this fingerprint looks more like a leakage, or this fingerprint looks more like a sensor fault. And now to formalize things a little bit, this is an optimization problem that we want to solve on a very abstract level. So we have our objective where we want to say, okay, we are looking for a simple explanation. Again, remember, there exist many, many possible explanations. So many possible explanations on how we could undo the event, so to say. But we want to pick the simplest one. And of course, we have to formalize what simple means in this context. And I will show you one straightforward way how this can be done later on. And then we have our constraint, which is then the contrastive property. So this property states that for all our models, so for all our virtual sensors, the difference must be sufficiently small. So it must be below some threshold. This is then where, like, the kind of ensemble constraint comes into play, because really the only difference to the optimization problems from before is that we have now this quanta over all models in our set of virtual sensors. Now, this, of course, is a pretty strong constraint, and it might not be possible to satisfy those. So this is why it might be a good idea to relax those constraints a little bit. So what we do is we add slack variables that allow constraint violations. And of course, those constraint violations are then penalized in the objective. But it adds some numerical stability to our problem and makes things actually feasible to compute in many settings. And then, of course, we have to think, like, how to implement this function psi here. So what does it mean to be a correct explanation? Well, in our case, this is easy. It means that the difference, so the distance between what we predicted and what we observed, must be smaller than some threshold. And then again, we have, like, this slack variable to allow for constraint violations. And this is, like, then a very general formalization of ensemble consistent explanations for regression models. Now, in our context, we implemented those virtual sensors as linear regression models. So very simple models. It's a linear combination on the input, basically, plus an offset. And now for the input, there are different choices. We could, for instance, decide to compute an average over some time window of some past sensor readings of some other sensors. We could, of course, also decide to stack all sensors together. And then, of course, we would increase the dimensionality of the problem a bit. We could also decide to include time if we think that this would be beneficial, or some other things. in all cases, we are dealing now with a linear prediction for the virtual sensors. And now we have this optimization problem, and now we can plug this into this optimization problem, and then we get actually either linear or convex quadratic optimization problems. And here I decided in the objective to use the Euclidean distance as a distance measure. You might also use other ones, but it is a common choice to do if we don't make any assumptions about the input domain. And now this is an optimization problem that we can solve. So we can use efficient solvers for convex optimization, like some interior point method or some simplex methods or whatever your favorite solver is. Or we could also use a method called nearest unlike neighbor method, where we basically do not generate an explanation, but rather picking an explanation from a set of already existing measurements. And this can become a pretty handy baseline because it automatically ensures plausibility if we can guarantee that the data set or the database that we use for generating the counterfactual contains only plausible measurements. Now, and then like what I said, like here we generate something, we have like this domain RD, and here we just pick something from a database. This is the only difference basically. And now in our case study, as I told you, we are considering L-town, and we have 29 sensors in our case, and we want to differentiate between sensor faults and leakages. And for this, we employ the method that I just described to you. And without going too much into the details of the method, I think the core idea are those ensemble consistent counterfactuals. Everything else is not too complicated that we build around it. I would like to show you a few results here. So here on the left-hand side, I have the illustration of a counterfactual for a sensor fault. And what I show you here is on the one side, the topology of the network, and also the sensor location denoted as those pink stars here. And then I show you the counterfactual as the changes that I have to make to the pressure readings of those sensors in order to undo the observed anomaly. And you can see here that in the case of the sensor fault, all the changes are concentrated on the faulty sensor, which makes sense because this fault in the system should be easily corrected if we just fix the single faulty sensor. On the other hand, here on the right-hand side, I have a leakage. So the leakage is placed here. And now we see that the counterfactual explanations, the changes are distributed among nearby nodes. So you see that like the three closest nodes, or maybe like also this one, the fourth closest node, they get the most changes. So here basically, the explanation tells me that I have to fix multiple, or I would have to fix multiple sensors, so to say, in order to undo the event. And then, of course, we could say, okay, how likely is it that all those 3 or 4 sensors have a sensor failure at the same time? Probably it's somewhat unrealistic. Then maybe it's fair to assume that there is something else going on. In our case, there's a leakage is going on. And then this is something like that provides us with insight of, okay, like what is going on and also where is it going on? Because you see like the counterfactual is also pretty good in localizing the leakage in this case. Now, to summarize, I just presented you a way or like a framework on XAI for interpretable event diagnosis. In particular, we talked about counterfactuals for reasoning over events. And here we always looked into the case of having like a residual-based event detection system. So we always have an observation, we have a prediction, and we want to explain the difference between those two quantities. And the method I presented is somewhat basic as the first steps towards this direction. I think as a next step, it's really important to think about context-aware explanations. And this is an open topic in explainability in general because most of these methods are generic. So they do not really know much about the domain, and they also often fail to consider time as an additional component. However, when it comes to critical infrastructure, time is usually a crucial component because often we model our system as a dynamical system where we cannot simply ignore time. Unfortunately, many XAI methods are not that good in dealing with time or also dealing with domain knowledge. So I think this is an exciting area for future research. Then, of course, also other domains. So in our work so far, we were only interested in hydraulic events, so like leakages, demands, sensor faults. What we also want to do is we want to move into water quality as well, and then work on explainability methods there. And this is an interesting domain because it's not only different from the hydraulics, because like in hydraulics, you often have like steady state simulation, whereas in quality, we don't have a steady state. But also the dynamics are much more complex. And I would guess that in water quality, we really have to incorporate domain knowledge into the XAI methods. We cannot like ignore it, like just put a simple proxy on top of the method. And for this water quality, we are currently running a competition at ICHCAI, where basically participants have to control the water chlorination of a network. And the competition is running right now. Submission deadline is today or tomorrow, depending on which time zone you are. So if anybody in the audience is participating there, please don't forget to submit your results. And what we want to do is we want to use the results from this competition and also like the benchmark itself as a starting point for investigating trustworthy AI in this water quality domain, which I think is not only super exciting, but also a very important application in practice. And then lastly, evaluation is also super important. Because the best explanation method is kind of useless if we cannot communicate it properly to the user. And on my previous slide, I showed you like those two visualizations where I had like the network topology, and I plotted basically the change recommended by the counterfactual on top of the topology. This is one way how to visualize this. This is what we came up with. It's for sure not the only way how this could be done. We are also preparing a user study where we want to investigate this usefulness in collaboration with some real operators. And but this is always a bit tricky because like when solving optimization problems, we can compute gradients and things like that. But when working with humans, we have to be really careful on like how we present things to them, and like also how we ask them for their feedback in order to get something meaningful back in the end. So evaluation is, I think, also a big problem, also for the XAI community, because it's often unclear like how we can evaluate the usefulness of explanations. Often we try to come up with like kind of proxies, like is the explanation correct, yes or no? But whether it's really like understandable or useful to a human, this is really difficult to evaluate. So I think developing some metrics and also benchmarks in this area would be super helpful and for sure necessary in order to advance the field there. All right, so this concludes the presentation so far. As promised, I have here a QR code to the slides, and I will also put a link to the slides into the chat. And then I would say we move on to the hands-on session. I think we still have like maybe 10 to 15 minutes left, if I'm not mistaken. And then afterwards, we can take questions. And for switching to the hands-on session, I will have to stop screen sharing in a second. But first, here you have the QR code to the hands-on session. I will also put everything into the link right now. But then I have to stop screen sharing for a second because I have to switch screens. So just give me a second. All right, so this is a link to the slides, which is a PDF file of the PowerPoint I just presented. And now comes the link to the hands-on, which is a Jupyter notebook. Again, just a second. Here you go. And now I will stop sharing and start sharing my other screen. So you should now be able to see my my Google Colab. Can you please confirm?
Yes, we can.
All right. So I mean, just a few comments there. I put this this notebook on a GitHub repository. You can also just view it here in Google Colab, even without having to log into your Google account. If you want to execute or to run the notebook, so if you want to follow along with the things that I will do in a second, you have to log into your Google account, but you don't have to, because I will run everything here on my screen, so you can just relax and see what I do. But like if you want to try out things yourself, you have to log in with your Google account. Now, this notebook is basically kind of an illustrative example of the concepts I just presented to you. And it's really just like an illustrative example. So it's not meant like to be like a product ready for deployment or so. There are many things that you could change or that you could improve. Now, the notebook, first of all, of course, we have to install some dependencies here, and I try to keep things to a minimum. So we have to install Flow, which is a package which I'm developing. It's basically a Python interface for EPANet. It's a high-level interface. So it tries to abstract away from many details and make things as easy as possible, while still, maintaining or like keeping the option to interact with EPANet directly. And then we have a package called CVXPy, which is a package that I think at least originally was developed by people at Stanford University. This is a package for convex optimization. So this basically can be used to solve convex optimization problems like the one for computing those ensemble consistent explanations, as I was showing you before. I already executed this line of code beforehand because it might take a bit of time to install all those dependencies. And then you also have to clone the GitHub repository. And here now you also have the link to the GitHub repository. So if you want to browse the repository there, feel free to do so. The reason behind this line of code is that we have to import some Python modules that I wrote just to keep this notebook to like keep it kind of clean and not too messy, such that it's still possible to understand things. So I also did this ahead of time to make sure that everything is there when presenting this. We have to include to import some methods. Should be also pretty clear for those people working with Python. Now, for the data generation, in this example, I decided to go for LeakDB. So here I have a plot of the topology of LeakDB. And in this scenario, I have 5 sensors placed in this network. So those orange nodes are the nodes where I have a pressure sensor. And then I generate a couple of scenarios here with my code, which I implemented using Flow. I think I will not go into detail how to generate this code because it's just like simple scenario simulation. If you have a question, I mean, like you will have to continue to ask me questions very soon. And if not, like you can just check out the code on yourself. So this basically allows us to generate scenarios from LeakDB and also simulate sensor force or leakages. And in this case, I just simulated 3 scenarios, which will be used for like calibrating my event detection method. And then I have a final test scenario, which will be used like to evaluate the event detection system.
Dr. Andre, could you please zoom in a little bit?
Sure.
Maybe just control and scroll the mouse. Yeah.
Does it work?
Yeah, this looks awesome. Thank you.
Okay, right. You're welcome. Yeah, so as I said, we generate some scenario data, and then we can inspect here the test scenario where I just plot the pressure over time at my pressure sensors. And you can already see, like, this is really an illustrative example because we can clearly see where the sensor fault is happening. I mean, here we get like negative pressure sensors, which of course is super unrealistic in practice. So it's a really really noisy sensor fault, so to say. So it should be easy to spot. But again, it's for illustrative purposes for this method. But all the other pressures, they behave as expected. We have like this quite regular pattern. It's a periodic pattern here. So looks good overall, except those faulty sensors here, which are at node 10. Now, I also have here a method for like process the data. So I decided to aim for a time window approach. So like I have a time window which goes over my data and then aggregates everything into a single feature vector, so to say. And yeah, I mean, it's also nothing fancy going on over here. I mean, like we grab our samples, we have to do some feature engineering. I did the most straightforward thing you can do. I just take the average, and this I do until I'm running out of data, so to say. Pretty straightforward, nothing fancy. And again, like this would be, of course, something that you would have to improve if you want to apply those methods in practice or like also in other use cases. And yeah, now the interesting part is, I think, the event detection method. So here I just wrote down what we are aiming for. Again, like we want to build this function f, which takes in our input features, so which are like just an average of the other sensors. We compare it to our observed sensor readings, and whenever the difference is too large, we raise an alarm. And yeah, so this can be then also implemented in Python. Again, like I would skip the implementation in interest of time. I have here an interface which should be somewhat straightforward. I have an ensemble system here, which basically implements all the virtual sensors for you. It has a function fit, which basically means you calibrate this virtual sensors on your training data. So like you need like a set of training data on a fault-free time window, and this is used like to build those virtual sensors and to also to estimate this threshold theta here, because this obviously is a super important parameter when it comes to the event detection method. And yeah, once we have this done, we can then apply this detector. Again, there's a function for this to our data. And then we get suspicious time points back. Yeah, so we have our input data and we have like our observations. So this is what the sensor values should look like. And then the method basically tells us at which points in time the difference between the prediction and the observation was too large. And here you can see it spotted something very quickly, which is no surprise because as you saw in the beginning, it's very noisy, a noisy sensor fault that we had here. Now, now we want to explain those detections. So now here we detected something, and we want to understand what we detected there. And here I have again the optimization problems. So the first option is that we could solve this convex optimization problem here, which would then compute an ensemble consistent explanation. So here it's just like it's a generative approach. We can come up with arbitrary changes to our pressure sensors. However, they must satisfy the event detection method in the sense that they must undo the event. So after those changes are applied, the prediction must be very similar to what we observe. So it must be smaller, or the difference must be smaller than this delta I. As I mentioned before, alternative to this is we just have a data set. So we could, for instance, just use our training data set and say, like, okay, pick the sensor readings from the past that would like kind of undo our observed anomaly. And again, I implemented everything for you. It's already there, so it should be straightforward to use. Okay, this is like a technical thing. I have to wrap my models in such a way that I can build my convex optimization problems. And but once I did this, I can just iterate over all my suspicious points in time. I get my input and my output, and then I compute a counterfactual. So here I compute an ensemble consistent counterfactual using this convex optimization method. And then I get back the final data point and also the change that is applied to the original sensor readings. And here what is commented out is basically the approach of the nearest unlike neighbor approach, where I just say like, okay, please give me the example from the past that most closely matches my observations, so to say. Then, in order to prepare for the visualization, I normalize the changes. So those changes, of course, could be positive, could be negative. They might say, okay, we have to increase some sensor readings or we have to decrease some other sensor readings. And of course, the order of magnitude might also differ. In particular, this might differ a lot when you have, for instance, different types of sensors. So if you have sensors that work on pressures and if you have flow sensors. Usually, like the magnitudes are very different there, and then it might be very difficult to spot the differences in the explanation. So this is why I normalize everything. So I say, like, okay, 80% of the changes goes here, 20% goes there, and that's all. And this is something then this is easier to visualize and probably also easier to understand. So this is what's happening there. And then lastly, I can visualize those. And this is then a very simple plot here. I have here on the x-axis the different sensors. So those sensors are the input to my event detection system. And then on the y-axis, let me scroll a little bit up, I have the normalized amount of change that has to be applied to each of those sensors in order to undo the event. Now, what does it tell us? It tells us that all the change, 100% of the changes has to go to node 10, so to the sensor at node 10. And this makes sense if you recall that we indeed had this very noisy sensor fault at node 10. So here it tells us that, okay, in order to undo the event, you have to change the readings at node 10. And this perfectly makes sense to us, I would say. Now I can also show you very quickly how it looks like when we do the nearest unlike neighbor approach. So just run everything again. And there you will see that things look a bit more noisy because instead of computing like something exactly, we just try to find the closest match from a database of existing cases. But the idea will be the same, kind of, or the message will be the same that we get. Okay, it takes a moment for everything to run, but should be there in a minute. There we go. So you see the story is still the same. So almost all the changes, they go to node 10. Again, this makes sense because this is where this huge sensor fault was. But there are also a little bit of changes applied to the other sensors, which can be explained due to the uncertainty and because, like, the system is changing over time and we will not be able to find exactly the same state again in the past. We might find something similar, but not exactly the same. And this is why we also observe a little bit of changes in the other sensors, but most of the changes go into this node. So I think the message is also pretty clear here that maybe we should inspect the sensor at node 10. Yeah, all right. This was a very quick hands-on or very quick illustration of how to do things in practice. And I think I'm done with that. So now I thank you for your attention, and now more than happy to take any questions you might have.
Thank you so much, Dr. Andre, for a very thought-provoking session. It's been very exciting to see how exploring the openings, like opening the AI box, the black box, and then see that we can have more trust and understanding about what it is doing. So we have gathered some questions from our audience, and I'll go one by one for them. So the first question is, how do you determine the optimal time window of past data to actually balance the model accuracy and interpretability?
Yeah, so I would say it depends. So I think, like, in general, there is like no general rule that you can use. What I would recommend to do is, like, I would recommend to simulate a few faulty cases, and then just try out different time window sizes and see how well you perform on those simulated cases, and also how happy you are with the explanation. Because for those simulated cases, like what I basically just showed you in the case study, is that you know the ground truth, right? You know, like, is it a leakage, is it a sensor fault or not? So you can judge the explanation. And I would suggest to just generate data and fine tune it on that one, because in practice you don't have the ground truth, right? So then you have to rely on your model.
I agree. There's another question, which is how often do we need to retrain the model to preserve both performance and explainability over time?
So I would say that retraining the model is most important for maintaining the accuracy, so predictive accuracy. It's not so much impacting the explainability or interpretability of the model. Of course, like when the accuracy of the model, so the predictive performance drops, then also the explanations might not look that good anymore. How often we have to retrain the model, I would say depends on the model complexity. So I decided to go for a linear model, which is the most simplest model you could go for. And of course, like a linear approximation of any dynamics is a very poor approximation, which might be only valid for a very small time horizon. So there you might want to update your model more frequently, or you might want to build several models. So let's say you build like models for different daytimes. Let's say you have a model for the night and you have maybe like 2 or 3 models for different periods of daytime where maybe like more complex dynamics are happening when people are actually consuming water. Or you might decide to aim for like more complex models where you don't have to do that much retraining. At this point, it might be also interesting that some models can retrain or update themselves automatically. So there are like some models or like some class of models. They are usually referred to as online learning or continual learning, where you train the model once in the beginning, but then while you are like applying it on your data, you keep feeding it more and more data and it keeps learning over time. So there you basically are constantly retraining and constantly adjusting your model. So this could be also something worth trying out. There, of course, you have the risk, like what I mentioned in the beginning, robustness issues. If your model is changing like every minute or so, then you observe an explanation right now, it might be already invalid in the next time point. So there you have to really balance between those two aspects, I would say.
Well, this means that we still need to think about how to use them in real-time applications and then have strategies for retraining them. That's a great
Definitely.
summary of the presentation, actually. The next question is, as you mentioned that the false data injections in water systems or the data poisoning impacts the counterfactual explanations. So how can one validate the robustness of or assess the impact of poisoning on the counterfactual explanations?
Yeah, this is a great question. This is currently something I'm researching.
Mm.
So I mean, so the short answer is I don't know. So right now we know that this data poisoning is a threat, but we don't have a defense method that is guaranteed to work. So I was investigating outlier detection methods. So like you take your training data set and you check for like any suspicious data points in your method, in your data set. And there are methods called outlier detection or anomaly detection method that can do this for you. However, you can do the poisoning in such a way that they also fail. So right now, my recommendation would be, if you're working in a critical application, to not use any AI methods if you cannot ensure the integrity of your data. Because it's not only that the counterfactuals can be manipulated. This is what I was researching because counterfactuals are like my favorite type of explanation. Also, other types of explanations are vulnerable to such data poisonings as well. And also the machine learning models, so the neural networks, the linear regression, whatsoever, they're also vulnerable. So right now, and this might be a bit disappointing to some of you, it's really, if you cannot ensure the integrity of the data, do not use any AI methods.
I see. So I think this is the bottom line for today's meeting that you should have trust in the data first and then
Right,
go for
right.
the
This is super, super
interpretability.
important.
All right. So the next question is about the residual based approaches. How do you set a robust threshold for understanding the change between the predicted and the observed measurements?
Yeah, so what I did in my code, and I mean, you guys will be able to look it up in the GitHub repositories. I was investigating the standard deviation or the variance, if you like, on the training data or on the validation data set. And then I say like, okay, I want to pick the threshold such that all my training data points are kind of not classified as faulty or that like there is no alarm being raised because
Hmm.
I know that there shouldn't be, right? I simulated them. I know they're fault free. So the method should not raise anything there. And then, of course, like what I mentioned to one of the previous questions is you can then, of course, also simulate some faulty data sets where you have like a sensor fault, a leakage whatsoever. And then you could use this also for further like determining the optimal value of the threshold. And maybe also as another comment, it might be also good, like if you go for this virtual sensor approach where you have like one model for each sensor, you might want to have different threshold for different sensors, just because you're like in some areas of the network, more dynamics are going on, or I don't know, maybe the pressure sensors are working better than the flow sensors whatsoever. There are just so many things that can happen. So you might want to pick like a local threshold and maybe also a time varying threshold. Like if you investigate your data and find that like the variance or the standard deviation or the uncertainty is like different over time. This could also be could also happen. So I think you really have to investigate the data and the models to come up with a good threshold there.
I agree. I guess the time varying threshold setting would be most appropriate for water distribution systems since we
Yeah,
have a different daily pattern, consumption patterns, and that explains more about the failures and other
right, right.
events.
But the
Thank
nice
you.
thing is, the method doesn't change. So it's just like a threshold you pick there. You
Yeah,
just have to pick the right one for the right time.
I think this is where you talk about the human-based interpretation, and then the human decision is more come into play, what threshold to choose than a machine learning modeler to explain what it
Yeah,
should be. Thank
yeah.
you. Another question is undoing events for preparing non-anomalous training dataset for regression-based anomaly detection method is a recommended approach to automate training data selection process.
Recommended approach. So this is a good question. I have to confess, like I'm like a machine learning researcher, so I don't have much experience with like deploying those things in reality. I talk to people that are working in the real world on this, so like companies working with water networks, or recently also I talked to people working on power grids. Whether this is something that they would approve, I don't know. To me, it sounds a bit risky, to be honest. But I also know that there is usually a large sim to real gap. So those simulators, they are nice as a playground to generate tons of data. So I think my feeling would be I would try to rely as much as possible on simulators and then maybe do a little bit of fine tuning on like real data, just to like kind of make sure that my model transfers to the real world in some sense. But yeah, it might be better to talk to people that are actually using those things in practice, I guess.
I see. Thank you. And we have the last question, which is
Mhm.
very interesting. Are any kind of black box behavior prevention or explainable AI implementation routine is available?
To what?
Are there any kind of black box behavior prevention or explainable
Prevention.
AI implementation is
Um,
available?
yeah. So people try to build models that are like guaranteed to satisfy like some behavior that was like predefined by, let's say, the engineer, or like kind of a requirement. The simplest requirement you can think about, for instance, is monotonicity. So like you would assume that like if you have, let's say, I don't know, like you observed a fault, and you would say like, okay, if I make this fault larger and larger, you would assume the methodology to still like raise an alarm, because if it once raised an alarm, you know, like making the fault even bigger should still result in a raised alarm. Um, this is of course a very simple one, but it can be already quite challenging for complex models like neural networks, because those models, they are super complex and it's really difficult to really enforce something there. There exist also other branches of work where they try to enforce counterfactuals. So they try to enforce that certain types of counterfactuals will be always valid. However, the works that I'm aware of, they do this at an empirical level. So they show a good performance, but they cannot like guarantee it from a formal point of view. So like there's no formal guarantee that this will always be the case. So yeah, those constraints, I agree, it's something really interesting, something maybe that we should have, but from what I know, we are still far away from having those. So it's still kind of an open research question to do this.
All right, thank you so much. Thank you so much, Dr. Andre, for a great presentation. You have actually answered all of the questions.
Mm. Right.
So before we wrap up, I have a quick few updates for all of you. So if you can see my screen now, try to, if you want to see our previous webinars on YouTube, please scan the QR over here and don't forget to follow us on LinkedIn and Instagram. If you want to join us and would like to stay tuned about our upcoming events, please do sign up for our mailing list. And if you have any feedback, do email us on wdsagradstudents@gmail.com. Once again, thank you so much, Dr. Andre, for your amazing presentation and all of you for attending. It's been a great one, and I would like to see you all in the next one. Thank you so much, everyone.
Thank you. Thanks for having me here, and have a great one. Bye.
Bye bye.